Hello, in this screencast we will introduce precise language to describe the long-term behavior of an exponential function. When we say long-term behavior, we are considering the behavior of the function as the input gets bigger and bigger. We have already established that any exponential function of the form f of t equals ab to the t power, where a and b are positive real numbers with b not equal to 1, is always concave up and is either always increasing or always decreasing. We see from their graphs that the long-term behavior of the increasing and decreasing functions is different. So the question arises, how do we precisely describe the behavior of f as t gets bigger and bigger? To start, let's consider the exponential growth function p of t equals 1.5 raised to the t power, and its respective values at t equals 10, 20, and 30. We see that the output of the function gets very large very quickly. In addition, there is no upper bound to how large the function can be. Indeed, we can make the value of p of t as large as we'd like by taking t sufficiently big. Therefore, we say that as t increases, p of t increases without bound. Next, let's consider the exponential decay function q of t equals 2/3 to the power of t, and its respective values at t equals 10, 20, and 30. We see that the output q of t is always positive, but getting closer and closer to 0. Indeed, we can make the value of q of t as small as we'd like by taking t sufficiently big. Therefore, we say that as t increases, q of t approaches 0. To represent these two common phenomena with exponential functions, the value increasing without bound or the value approaching 0, we will use shorthand notation. First, saying as t increases, q of t approaches 0 is equivalent to saying q of t tends to 0 as t increases without bound. It's natural to write q of t tends to 0 as q of t arrow 0. Since we have the notation of the infinite to represent quantities without bound, we can use the symbol notation for infinity and arrow notation to write t increases without bound. So then in a similar way, saying as t increases, p of t increases without bound is equivalent to saying that p of t increases without bound as t increases without bound. And the notation would be p of t arrow infinity as t arrow infinity. But again, we would say that p of t increases without bound as t increases without bound. In conclusion, we can summarize the long-term behavior of exponential functions this way. Let f of t equal b to the t power with growth factor b greater than 0 and not equal to 1. If the growth factor b is between 0 and 1, think exponential decay, then b to the t power tends to 0 as t increases without bound. If the growth factor b is greater than 1, think exponential growth, then b to the t power increases without bound as t increases without bound. Up to this point, we have identified when exponential functions are increasing or decreasing. The exponential functions are always concave up, and now we have precise language to describe their long-term behavior. Next, we will combine what we've learned about basic exponential functions and transformations of functions so we can eventually model real-world phenomena with exponential functions.